Hello everyone and welcome to today's webinar where the subject will be simulation for the hydrogen ecosystem. I'm your presenter. My name is Anthony Lorella and I am the lead systems presales specialist at Maya HTT. At Maya HTT, we help organizations with their digital transformation journey. We've been recognized by Siemens as a top global partner, but we're not just a consulting and systems integrator. We also develop software with over 30 modules authored for Siemens, used by millions worldwide. At Maya, 75% of our employees are scientists and engineers with hands-on experience in nearly every industry. Whether an organization is looking to better design, simulate, manufacture, or optimize operations, our combined engineering, software development, and AI expertise uniquely position us to move you from concept to completion and beyond. First, let's consider some of the challenges for hydrogen. Hydrogen is one of the best solutions to overcome today's constraints regarding the reduction of CO2 and pollutant emissions. One of the most promising solutions comes from the effort to generate green hydrogen through water electrolysis using green electric power. Hydrogen becomes an even more interesting vector when new solutions are developed to generate it, replacing the steam reforming of natural gas. These days, we often consider hydrogen in the transportation industry, including automotive, trucks and buses, and trains, aircrafts, and even ships. But hydrogen is also a solution for generating heat and power in large power plant or local power production for factories, data centers, and even homes. Now, let's consider how simulation can help to address the hydrogen industry challenges. With simulation at large, we have a typical set of challenges to overcome. For example, what effect do changing conditions have on my system's performance? How should I size my components relative to performance requirements? What about auxiliary systems like thermal consideration or even cost? And how can I predict and control conditions such as pressure, flow rate, and temperature without a prototype to test? Modeling and simulation offer a quick and effective way to assess the performance of many systems, including those in the hydrogen industry. They allow us to predict real-world behavior, improve efficiency, and ensure reliability, and evaluate multiple configurations, all while minimizing cost. Any and all of these are possible given the simulation capabilities offered by Siemens SimCenter solution. The SimCenter portfolio includes all products related to simulation and test, that is, system simulation, CAE simulation, and physical testing, with exploration and analytics and data and process management occurring across all three of these pillars. We'll focus today on the system and CAE part, highlighting the diversity of the hydrogen applications that can be solved with such an approach, which can execute the digital twin in a few seconds, minutes, or more. Here we see just a few of the examples across the hydrogen industry where simulation can play a part. We'll start with hydrogen production, including electrolyzers. Then we'll go on to renewables, which can feed energy for the production. We'll move on to fluid transport infrastructure and the different methods in there. Then we'll go to storage, tank modeling, and hydrogen refueling. And then we'll move on to fuel cells, hydrogen combustion, and then other applications across industries. So let's begin with looking at how simulation can help you produce a digital twin, first for green hydrogen production. With our system simulation tools, we're able to model all parts of the hydrogen production network, including alternative energy sources, electrolysis, and onto storage. These system simulation tools are able to predict in seconds the distribution of hydrogen production over a period of months, with mixed energy sources coming from things like wind turbines, solar panels, wave energy converters, and more, and then feeding energy to the electrolyzers to store the energy afterwards in hydrogen tanks. The model shown here is used to perform a simulation across 1 year to predict the interaction between wind, waves, and the sun to feed an electrolysis system and then a pressurization system to feed the produced hydrogen into storage tanks. We can then look at the efficiency and production of hydrogen based on the different weather conditions and place that in different localizations where weather conditions might vary. So you can see here an assessment across a year in terms of the contribution of different green energy sources and how they fed into the system for the production of hydrogen. If we wish to look at a more component level in more detail, then we can use something like CFD to do the simulation of the electrolyzers themselves in much more detail and spatial resolution. Now let's consider our second example, digital twin for fluid transport infrastructure. There are a number of different possibilities for modeling and simulation to come in for the transportation infrastructure. First would be transportation of purely gaseous hydrogen, where we can look at things like sizing and selecting compressors, looking at the valve conditions for flow and pressure drop across the system. For liquid hydrogen transportation, we can do other things like heat exchanger selection and design, looking at operating conditions to avoid things like pressure surge, and also being able to predict cavitation and flashing, and then evaluating methods for mitigating that. Other options include simulation for chemical carriers for hydrogen, where we have to model complex branch systems and maybe automate the balancing of the different lines that are included. And then also there is compression, where again we would have to do things like sizing and selecting heat exchangers, looking at overall efficiency of the system and maybe incorporating waste heat recovery, and then also doing some work in predictive simulation for minimizing the different losses across things like fittings in the system. On the storage side, we can use simulation for tank filling, which can allow us to model and capture things like pressure rise, temperature evolution, which in storage can reach critically high values, as well as capturing the buoyancy effects, including stratification of the fluids in the tank. Additionally, the SimCenter portfolio offers a complete solution to cover the end-to-end simulation process for something like hydrogen storage. We can cover the component design thanks to a strong CAD integration, leveraging our best-in-class finite element preprocessing, and then also our capabilities for the simulation for composites manufacturing and the simulation of composites in a structural context as well. All of this can come together, for example, in the problem that you see in front of you, which is the structural analysis of a Type 4 storage tank made with composite materials. The fourth use case I'll introduce today is one of the digital twin for fuel cell systems integration. SimCenter comes with a set of models and tools dedicated to the fuel cell stack simulation, from functional models to more advanced ones integrating more and more physics at each step. Basic stack design is possible, integrating electrical systems like the battery integration, DC-DC converter design, or even motor inverters. Looking at thermal management of the entire system, predicting stack temperature, looking at thermal exchanges and cooling options. Modeling of the air and hydrogen loops to look at the dynamic gas flow and the composition of those, including humidity management. Extending the simulation to the powertrain for electric motor and driveline design, as well as the overarching controls for different energy strategies, and also for the strategies for the feeding of fluids into the fuel cell. All of this can come together, either one or all, to represent subsystems and their interactions and integration together. When you need to go deeper into detail with the design of the fuel cell system, you can integrate more physics into your model. Instead of looking at just the fuel cell with a single component, you can integrate more details and consider even more subsystems and add them as your project matures. You can now evaluate the interactions between stack, cooling system, air and hydrogen feeding, and the extended complete electrical network. With this type of model, you can also more accurately evaluate the stack performances and losses, taking into account temperature, pressure, gas composition, and humidity. This type of model also makes it possible to evaluate the impact of the compressor and other controls on the whole performance of the stack, and the impact of these controls on the efficiency of the entire system. Again, if we want to go to the geometry level, a more detailed analysis is often possible with CFD as well. Modeling of fuel cells with CFD allows for single phase for particle exchange membrane, where any number of reactions can be specified. Multi-phase flow for particle exchange membrane fuel cells as well, where we can look at flooding and membrane dryout. We can even predict parasitic reactions for the lifing of the fuel cell, or just tracking things like sorption. Additionally, we can do single flow for solid oxide fuel cell analysis, once again for modeling any type of reaction, and also electromechanical and ohmic heating can be accounted for. Now we'll move on to simulation for hydrogen consumption, and here we'll split this into two parts. First, we'll start with the stationary applications that we mentioned before, like combined heat and power, and residential applications. So for this first example, we can extend the scope of our simulation efforts by looking to include the entirety of the infrastructure in question. We can incorporate the consumers at a grid level, both local and large-scale consumers that can use stationary fuel cell systems, and these have significantly different objectives than their counterparts in the hot transportation industry, which we will see later. So in the example we see here, we're looking at a green hydrogen-based microgrid that was built up using system simulation. More of the focus is put here on the electric side by modeling, for example, the microgrid that we can see, the DC-DC converters and other components as well. Ultimately, the goal of this model in particular is to optimize the global system efficiency and consider thermal management. We can see here the breakdown of energy across either a day or at the month level across a year. Here we see a second example where we've taken a solid oxide fuel cell in a combined heat and power residential system. This model differs slightly because its objective is to show a system model of the complete residential system with reformers, afterburners, batteries, grids, loads, and controls, where we're actually looking to evaluate the total cost of the energy production depending on the energy mix across a year. So as a counter to that, we can move on to the digital twin for hydrogen consumption, this time in terms of the transportation industry. And here we can see examples for not just the vehicles that use them, but also refueling. So we can consider the following challenges for refueling stations. Refueling time is critical and needs to be close enough to conventional methods to be worthwhile. Energy consumption needs to be reduced and mitigated as much as possible. Safety is of utmost concern and must be validated for all different scenarios. And obviously cost minimized as far as possible without impacting quality. So all of these can be assessed by looking at a system architecture in terms of the entire refueling station, and we can see that here in this example. This allows us to do some basic analysis which will inform component design and sizing of things like heat exchangers, compressors, and valves, as well as evaluating different control strategies in this system. So do we need to include multiple compressors? Do we need accumulators or buffers in the system? How many vehicles can we realistically connect? So on and so forth, as well as evaluating different alternatives for the architecture and then performing robust analysis and optimization as well. So a model like we previously saw can give us a lot of useful information. The results of that model can allow us to quickly evaluate the evolution of pressures and temperatures of the flows in different parts of the system. We can predict the time it would take to fill a vehicle tank and then also recharge the fueling station's pressurized tanks and look at the temperature depending on the speed of the refueling and evaluate control strategies to manage that. Additionally, we can look at sizing the heat exchangers to keep the gas in the right operating temperatures depending on what part of the process we see. Also allows for the animation of a lot of these different parts of the process for better information delivery in terms of the results. Beyond just the modeling of refueling stations, we can also look at the integration of fuel cells in the actual vehicles. So in this case, those can be placed in any of the major streams of transportation, whether that's automotive, where we can evaluate vehicle type, road conditions, and the drive cycle's effect on the fuel cell. In the marine industry, where we can evaluate then things like sizing for the sea state, the propeller parameters, ship resistance, and the different missions, as well as aerospace, where we can also look at the flight mission, the power budget, the flight dynamics effect on the performance of the fuel cell. Beyond just modeling of the fuel cell integration into a vehicle, we can also do the simulation of hydrogen combustion, where we have things like modeling and simulation of hydrogen turbofans, where we can select the correct architecture, validate the on-design results, but also predict off-design performance and thermal considerations. Additionally, for the automotive sector, we have hydrogen internal combustion engines, where we can use a systems approach to study the coupling of the air injection and control, and then the also impact of air and fuel delivery on things like emissions. So in conclusion, simulation with SimCenter can really help address challenges of the hydrogen industry across the board. The extensive multi-physics platform can allow simulation of any part of the system or all of them together. It allows for sizing of subsystems and components and looking at various operating conditions. We can better integrate those subsystems at a really whole system level and improve performance in the short term or large scale for improving ROI. It allows for more detailed modeling of systems to really better understand component behavior or system behavior, whether it's at a microscopic or macroscopic level. And then those models can also serve an extended purpose in virtually validating control strategies against a model before prototypes are available. And then obviously for selecting the right design as quickly as possible, reducing risk and accelerating project timelines. That takes us to the end of the presentation. Thank you very much for your attention. If you wish to know more, please reach out to myself directly. You can find my contact information here. Or to learn more about MyIHTT, please visit www.myiHTT.com or use the QR code here to reach out if for any more particular questions. Thank you very much and have a great day.